Welcome back. Now today I'll be teaching you classification of functions. Now classification of functions, by this I mean identifying whether a function is one, many one, into or onto. Now as you can classify people on the basis of sex as well as on the basis of their food habits. Now, on the basis of sex, broadly we can classify people as male and female. And similarly, based on food habits, we can classify them as veg and non-veg. Now, similarly, functions can be classified based on two types. See, based on mapping. Now we can classify functions as one and many one. Now based on range and codomain, functions can be classified as into and onto. So you have two classifications based on mapping and you have two classifications based on range and codomain. Now we will learn in details about each one of them and how to identify them. But on this basis, I can say that functions can be categorized as a one function can be into as well as onto. Similarly, a many one function can be into as well as onto. So now, as the name itself suggests, what is a one function? One value of x corresponds to one value of y. Now, if this is true, then I'll say that the function is a one function. Now, here you will say that more than one value of x, corresponds to one value of y. If this is true, then you will say that this function is a many one function. Now, but this is just the definition and it is not at all sufficient to solve problems. So we need to go further into details of each one of them. So now let's get started with a one function. See, the alternate name given to a one function is also an injective function and a function which exhibits a one property. Now that is also called an injection from set x to set y. Now, onto function, the alternate name given is a surjective function. See, this is the case when range of a function is a proper subset of the codomain, and if range of a function is equal to its codomain, then the function is said to be an onto function. So let's start one function in details. So from the definition you get that if one value of x corresponds to one value of y, then the function is said to be an one function. Now in mapping, how does it look like? So a one function. Now in mapping, I can see that one value of x corresponds to exactly one value of y. Now this is how the mapping looks like. But for problem solving, now let us take a couple of examples. Suppose I take the example of e to the power x. E to the power x forms a graph like this. And fx equal to, say, e to the power minus x. Now e to the power minus x forms a graph like this. Now fx equal to x cubed. Now this has got a graph like this. And fx equal to minus of x cubed. Now it has got a graph like this. Now in both the graphs on the left hand side, I can say in all four of them, if I draw a line parallel to x-axis. See, any line parallel to x-axis means y equal to constant. See, the line of output, that is y equal to constant, it meets the graph at one point. That means this is the value of x which gives this particular value of y. See, here also there is only one value of x which gives you this value of y. Here also there is this value of x which gives this value of y. And here also this value of x gives you this value of y. So this is the simple graphical test whether it is a 1-1 function or not. So the best method to identify whether a function is a 1-1 function or not is graphical. Draw a line parallel to x-axis. If it cuts the graph at one point, that always means the function is a 1-1 function. Now let us think of other methods, because for every function you won't be able to draw its graph. Now I have taken two different y coordinates. See, f of x1, f of x2 here. Same way I can take two different y coordinates here also on any of these graphs. See, what is the thing common to all the graphs? See, any two different y coordinates on these 1-1 functions can be equal. If these points merge, that means their x coordinates are also equal. So when I say that f of x1 equals to f of x2, you should get the result x1 equal to x2. So let us form the equation f of x1 equal to f of x2. Now, if I take fx to be x cubed, this is x1 cubed equal to x2 cubed. So x1 cubed minus of x2 cubed is equal to 0. So x1 minus x2 into x1 square plus x1 x2 plus x2 square is equal to 0. Now naturally this factor, if I make it equal to 0, so x1 minus x2 equal to 0, this means x1 equals to x2. Now why I am not considering this factor? Because this gives you imaginary roots. So now look here, the equation f of x1 equal to f of x2 implies that x1 equal to x2, which I said in the graphical observation. So the second method of identification is f of x1 equal to f of x2. If this gives you the output, or this gives you the conclusion that x1 is equal to x2, then also I can say this function is a 1-1 function. Now, this method should be applied only for those functions whose graph you cannot draw, or functions which are discontinuous and non-differentiable. Now, see, there is a third method which is in fact the most important amongst all of them. Now, as you can mark, see, this function is always increasing in nature. See, this function fx equal to x cubed, it is also increasing. Whereas the two functions on the right side, they are decreasing. So all 1-1 functions, they will either be strictly increasing or they will be strictly decreasing throughout their domain. Now this is a very important aspect, because increasing and decreasing is a general terminology. It is not just restricted to differentiable functions. Now, but for differentiable functions, if we talk of, now what is the criteria for a function to be increasing? Many of you must have learned this, that if the first derivative is positive, then the function is increasing. And if the first derivative is negative, this means it is decreasing. But is this the complete criteria? Now, let us observe from these graphs. See, f dash x here is e to the power x, which is no doubt always positive. F dash x here is minus of e to the power minus x, which is always negative. So no doubt these two conditions are fulfilled. But let's come to this condition. f dash x is 3x square. Now tell me, no doubt x square is positive, but what about at the point x equal to 0? At x equal to 0, f dash x is also 0. So this satisfies the condition greater than equal to 0. So despite of this being equal to 0, you can see from the graph the function is always increasing. And here also f dash x is equal to minus 3x square, which is less than equal to 0. But still the function is decreasing. See, at 0 you don't get any critical point neither here or here. So how do I understand that despite of f dash x being equal to 0, I am not getting a critical point? See, the simplest way of judging this is by the sign of f dash x. Now sign of f dash x, it does not change at the point x equal to 0. Here also you can see at x equal to 0, the sign does not change. On both sides it's negative. So the complete criteria, so what is the true criteria for a function to be increasing or decreasing? That is a 1-1 function. See, I'll say this is greater than equal to 0, this is less than equal to 0. So that means if the correct criteria for a function to be increasing is f dash x should be greater than equal to 0 or f dash x should be less than equal to 0. And equality should occur only at those points where the sign of f dash x does not change. So if you have a differentiable function satisfying this criteria, then I'll say that in that particular interval the function is going to be a 1-1 function. So once again I'll repeat. Now there are 3 methods to identify 1-1 functions. The first method, as you can see, is graphical. If I draw a graph, draw a line parallel to x-axis and which intersects a graph at just one point, then the function is a 1-1 function. Otherwise, if I form an equation f of x1 equal to f of x2 and it gives the output x1 equal to x2, then I'll say it is 1-1. And the third and the most important method which is applicable for differentiable functions. If f dash x is greater than equal to 0 or less than equal to 0, then the function is a 1-1 function, provided the equality occurs only at those points where the sign of f dash x does not change. Now let's check on few problems. Now let us say I have a function fx is equal to, say, log of x plus root over of x square plus 1 with respect to base e. And I ask you to check whether this function is 1-1 or not. Now we can see this is a differentiable function. So if it is a differentiable function, f dash x is 1 by x plus root over of x square plus 1 into derivative of this. The derivative of x is 1. Derivative of this term will be 2x by 2 times root over of x square plus 1. Now if we cancel out this factor of 2 and take LCM, see, you get 1 by root over of x square plus 1 into root over of x square plus 1 plus x divided by root over of x square plus 1. Now you can see these two, this factor gets cancelled with this one and you are left with 1 by root over of x square plus 1. Now this is the positive square root and in the numerator you are having 1. So this is greater than equal to 0 for all x belonging to R. So if this is greater than equal to 0 for all x belonging to R, that means this function this function fx is an increasing function and it is always a 1-1 function. So I'll say that fx is a 1-1 function. Now let's move on to the next example. Now let us take a cubic. Now if I am writing fx equal to alpha x cubed plus 3x square plus 4x plus 5. I ask you find alpha for which fx is 1, 1 is 1, 1 function. Now a cubic polynomial is definitely a differentiable function. So all polynomials are differentiable functions, so I'll straight away apply the third method. So this will be 3 alpha x square plus 6x plus 4. Now fx is 1, 1 if and only if f dash x is greater than equal to 0 or f dash x is less than equal to 0. See, that's what I can say. So 3 alpha x square plus 6x plus 4 is greater than equal to 0 or 3 alpha x square plus 6x plus 4 is less than equal to 0. Now tell me a quadratic ax square plus bx plus c is greater than equal to 0 for all x belonging to R if and only if a is positive and the d is less than equal to 0. Correct? So this is a quadratic. Now this quadratic can be greater than equal to 0 only if 3 alpha is positive and 6 square minus 4 into 3 alpha into 4 is less than equal to 0. So we can cancel out, in fact, 36 minus 12 into 4 alpha is less than equal to 0. So 4 alpha is greater than equal to 3. So alpha is greater than equal to 3 by 4. Now you have 3 alpha positive and this positive. So what is the intersection of these two? See, the intersection of these two is 3 by 4 to infinity. Now let's talk about the second case. See, a quadratic ax square plus bx plus c is less than equal to 0 for all x belonging to R if and only if a is negative and d is less than equal to 0. So if I am using this condition over this, say 3 alpha is less than 0, that means alpha is negative and discriminant less than equal to 0 we have already solved. So this gives you alpha greater than equal to 3 by 4. Now is this possible that simultaneously alpha is negative and alpha is greater than equal to 3 by 4? No. They are contradictory conditions, so this is not going to hold true. This is the one which will be true. So I'll say that alpha belongs to 3 by 4 to infinity, then only this function is going to be a 1, 1 function. Let us take one more example. Now, suppose I am writing fx is equal to ax plus sin x, and I ask you again the same question, find a for which fx is a 1, 1 function. It's a 1, 1 function. Now the question arises, see, this is differentiable, this is also differentiable. So f dash x will be equal to a plus cos x. Now, can I write this as a minus 1 plus cos plus 1 plus cos x? See, this also can be written. I can also write this as a plus 1 minus of 1 plus cos x. See, either this or I'll write it like this. So this becomes a minus 1 plus 2 cos square of x by 2. Or I can write this as a plus 1 minus of 2 sine square of x by 2. Now observe this carefully. See, if this parameter is greater than equal to 0 or less than equal to 0, then either f dash x is greater than equal to 0 or f dash x is less than equal to 0. In both cases, my function is going to be a 1, 1 function. Now 2 cos square x by 2 is always greater than equal to 0. See, this parameter is always greater than equal to 0. And this parameter is always less than equal to 0. So if I can make this parameter greater than equal to 0, the function is always going to be a 1-1 function. If I make this parameter less than equal to 0, then it will always be a 1-1 function. That is, f dash x will be negative. So the basic criteria is a minus 1 less than equal to 0. So a less than equal to 1. Sorry, my mistake. Greater than equal to 0 or a greater than equal to. A plus 1, if I make this negative, that means a less than equal to minus 1. Then also your function is 1-1. So either this or this. So that means a belongs to minus infinity to minus 1, union 1 to infinity. So this is the set of value where this function is a 1-1 function. Now, there is another way of thinking it. You need not write from here to here. You just can calculate from here. Now, what is the alternate way of thinking? See, if I want f dash x to be positive, greater than equal to 0, what is the minimum value that cos x can have? After adding the minimum value, if it is positive, it will always be positive. So that means the minimum value of cos x is minus 1. So if a minus 1 is greater than equal to 0, that means a greater than equal to 1. Now, after adding the highest value, if something becomes negative, then it will always be negative. So what is the highest value that cos x can have? The highest value that cos x can have is plus 1. So this is less than equal to 0. So a less than equal to minus 1. So you can get your answer thinking like this also. And this is a general process which you should apply, that whenever you have sum of two different kinds of expressions, specifically if there is a trigonometric expression, consider the highest and the lowest values for getting it to be greater than equal to 0 or less than equal to 0. Okay, now let's move on to many-one functions. So as per the definition, a many-one function, now what does it mean? That more than one value of x will correspond to a single value of y. So it is possible that two values of x can give you this, or three values of x can also give you a single value of y. Or it is also possible infinite values of x can give you the same value of y. So if this is true, now let us take into consideration some common examples. So if I take fx equal to sin x, see, it forms a graph like this. So if this is the kind of graph that sin x has, in fact this graph is never ending, it will continue. So if I draw a line parallel to x-axis, see, it intersects at infinite points. That means what? There are infinite values of x which give you this particular value of y. Say for example, sine 30 degree is also half. Sine 150 is also half. Sine of 360 plus 390, that is also half. So there are infinite values of x which give you the same value of y. So more than one value of x corresponds to a single value of y. So I'll say this is a many-one function. If I take fx equal to x square, see, fx equal to x square forms a graph like this. See, every line drawn parallel to x-axis intersects this graph at 2 points. Here it will cut at 1 point, that is 0. So this is also a many-one function. Or I can say fx equal to mod x. Fx equal to mod x forms this V-shaped graph. And see, this also intersects at how many points? More than 1 point. So all of them are many-one functions. So this is the first method, the graphical method. Now, if the first method, again I'll repeat, if a straight line drawn parallel to x-axis cuts a graph at more than 1 point, it has to be a many-one function. Now the second point that comes into play. Now let us say this value is x1 and this value is x2. So this y is f of x1 and this y is f of x2. Now let us equate the two. See, no doubt that y coordinates are same, but are the x coordinates same? So on solving an equation f of x1 equal to f of x2 of this structure, see what do I am getting? Let us solve sine of x1 equal to sine of x2. So we can write x1 as n pi plus minus 1 to the power n times x2. Now is it necessary that x1 is equal to x2? No. So x1 is not necessarily equal to x2. So what is the conclusion you are getting? That f of x1 equal to f of x2 is possible, but that does not necessarily mean that x1 is equal to x2. So on solving an equation like this, if you get x1 is not equal to x2, you will say that the function is a many-one function. Now the third and the most important method, which we will be using very often. Now you can see on these graphs there are practically critical points present. See, this is a critical point. Now look here. See, these are critical points present on this graph. Now, how do I identify them? See, from here to here, this function is increasing, and at this point, from here to here, now it is decreasing. So at this particular point, nature of this function changes from increasing to decreasing. At this point, it changes from decreasing to increasing. So, what is the characteristic of this point? As you can see, if I have drawn tangents, they are parallel to x-axis. And any line that is parallel to x-axis has got slope 0. So these are the points where f dash x is equal to 0. In fact, we can check from here. F dash x for sine x is how much? Cos x. Now cos x is equal to 0 at x equal to every odd multiple of pi by 2. Every odd multiple means minus pi by 2, pi by 2, 3 pi by 2, 5 pi by 2. And you must be aware, see, if I plot the sign of cos x, see, between just less than pi by 2, cos x is positive. And after pi by 2, that means in second and third quadrant, cos x is negative. In the fourth quadrant, it is again positive. So at all points where f dash x is equal to 0, see the sign of f dash x is changing. This is the difference. So once you get real roots for this equation and the sign of f dash x changes across these points, so I'll say that the function is a many-one function. So once again, I'll compile the things. Now, how many methods are there to identify many-one functions? See, here also you have 3 ways to identify. The first method is graphical. If you draw a line parallel to x-axis, it will cut the graph at more than one point. That is the first identification mark. Second identification mark is, if f of x1 equal to f of x2, I form an equation like this. And on solving, you are getting x1 not equal to x2. So you will say that the function is a many-one function. Now the third and the most important method, but this is applicable only for differentiable functions. So better be careful while applying this. If a function first derivative of function equal to 0, this equation gives real roots, then check for the sign change across those points. If sign of f dash x changes across those points, then you will say that the function is a many-one function. So now let's take a couple of examples based on many-one functions. Now if I say that fx is equal to now e to the power x plus e to the power minus x by 2. Now check whether this function is many-one or not. So what I'll do, I'll first find out e to the power x minus e to the power minus x by 2. Now let's equate it to 0. So e to the power x equals to e to the power minus x, and e to the power x is 1 by e to the power x. So e to the power 2x is 1, so x equal to 0. See, f dash x equal to 0 is giving me a real solution. So if this is giving me a real solution, now I need to check the sign of f dash x across 0. Now what is the value? See, if I put a value of x less than 0, now let us say e to the power minus 1. Minus of e to the power 1, see this is certainly negative. So for minus 1, if it is negative, it will be negative. Now let us put a value 1. So e to the power 1 minus e to the power minus 1, see this is positive. So the sign of f dash x changes from negative to positive. So I will say that fx is a many one function. So this is how you will test. Now let me combine both the functions testing methods. See, if we follow the graphical way, then what we should do? Draw a line parallel to x-axis. If it cuts the graph at one point, the function is 1, 1. If it cuts the graph at more than one point, that means the function is many. Second method, let's solve the equation f of x1 equal to f of x2. If it gives you the solution x1 equal to x2, then the function is 1, 1. But if it gives you the solution x1 not equal to x2, then the function is a many one function. Now the third and the most important method, which we'll be using to the maximum extent. Now f dash x equal to 0. Now if this equation, it gives you real roots, then check for sign change. Sign changes, then you will say it is a many one function. If sign, no change in sign, across those roots, so then straight away you will say it is a 1, 1 function. If it does not give you real roots, that means if it gives you imaginary roots, so then you will say simply that this is a 1, 1 function. So in a compact way you can remember this and accordingly identify whether a function is 1, 1 or not. Now based on mapping, these are the two types, 1, 1 and many one. 1, 1 is also called an injective function. Now based on range and codomain, you have two types. So based on range and codomain, the first type of function that we get is an into function. Now what is an into function? Now if range of a function is a proper subset of its codomain, if range of a function is a proper subset of its codomain, then you will say that it is an into function. Now some common examples I'll take, but first let's see what kind of look does it give you in mapping. See, if I create a mapping like this, see there are a lot of elements which are left out. That means I did not get these elements as output. See, the left side you cannot have any vacant space element, but in the right side you are having. So these are the elements which I got as output, but these ones I did not. So this kind of mapping should be visible in an into function. Now practical terms, let us take the example of x square. Now fx equal to x square has got a graph like this. Now if fx equal to x square has got a graph like this, looking at the graph, now tell me what is the codomain of this function. I have not mentioned any set xy here. So by default the codomain is the set R, that means the entire y-axis. If I project this graph over the entire y-axis, see I get only this part, that is the positive part, 0 to infinity. So range of the function is 0 to infinity. That means what? Range of the function is the proper subset of the codomain. Now since it is a proper subset of the codomain, I'll say this is an into function. Let us take another example. Say if I write fx equal to sin x. Now here also what is the codomain? The codomain is R. because here also I didn't mention any set. Now suppose I'm writing, say I'm drawing the graph of this function. Sin x will form a graph like this. See, the whole y-axis is the codomain. Now what about the range? Sin x gives you values only from -1 to 1. So that means this function is, this part is certainly a subset of the entire codomain. So range of the function is -1 to 1. So range is a proper subset of the codomain. So this is also an into function. But what if I write like this, say fr to -2 to 3, where fx is equal to cos x. Now as soon as I have written this, see, I have specified the codomain to be -2 to 3. Now fx equal to cos x will form a graph like this. See, this kind of graph will be followed by cos x. Now what is the range of this function? See, -1 to 1. What is the codomain? The codomain is -2 to 3. See, certainly this is a subset of the codomain. So I'll say this is also an into function. Now I hope you have understood till here. Now let's talk about onto function. Now what is an onto function? See, any function where range of the function is equal to its codomain. If range is equal to its codomain, now that will be called an onto function. See, there are no elements left out in this set which do not have a pre-image. Now this kind of function is also called a surjective function. Now let us take some practical examples. Say fx equal to x cube. Now x cube will form a graph like this. Now I didn't mention any set xy here. So if I didn't mention any set xy here, what does it mean? The codomain is y-axis. And if I project it, it will cover the entire y-axis. So codomain of the function is R and range of the function is also R. See, the projection covers the entire y-axis. So this is also in fact equal to R. So range and codomain, since they are equal, you will say that this function is an onto function. Now fx equal to, say, let us take log x. Now log x has got a graph like this. Now if this is the kind of graph that log x has, see, if I project this graph, it will cover the entire y-axis. So since the projection of this graph covers the entire y-axis, I'll say range of this function is entire y-axis. So codomain of this function is R and the range of this function is also R. So this is also an onto function. Now all even degree polynomials. Now if I talk of a quadratic polynomial, it will be either like this or it will be like this. If I talk of a fourth degree polynomial, it will be something like this. Now can the projection of this cover the entire y-axis? No. It will cover only a part of the y-axis. So all even degree polynomials are into functions. Sorry, all even degree polynomials, all even degree polynomials are into. But keep that in mind that no set xy is mentioned here. Then this will be possible. But if I talk of odd degree polynomials, all odd degree polynomials are onto functions. So all even degree polynomials are into and all odd degree polynomials are onto functions. Now why did I say that? Now if I take the example of fx equal to, say, a linear function itself. So what kind of graph does a linear function have? See, it will be either like this or it will be like this. It depends on the coefficient of x. Coefficient of x positive means like this, So projection of this will cover the entire y-axis. A cubic generally has like this. A fifth order polynomial will form something like this. So it depends. See, it travels from minus infinity to infinity. So its projection will cover the entire y-axis. So that is why I said all odd degree polynomials are onto functions. Now if you have a function, something of this structure, say fx is equal to, in this format, a polynomial plus a simple polynomial combination of sin x and cos x. Remember, this should be a polynomial combination. So in this case, this polynomial decides whether the function is going to be into or out. Now if I am writing, say fx is equal to, say x plus sin x. Now what degree does this polynomial have? 1. That means it is an odd degree polynomial. So it will be by default an onto function. If I write like this, say 3x cubed plus 4x plus say sine cube x into cos square x. Now this will also be an onto function. But if I write on the other hand, say 2x square plus 4x plus 6 sine square x. Now what is the degree of this polynomial? The degree of this polynomial is even, so this will be an into function. So I don't think that you should be having any confusion. So if the polynomial, this polynomial is of even degree, this entire function fx is going to be into. If this polynomial is of odd degree, entire function is going to be onto. So now let's move forward in classification. Now based on mapping, we had two types, 1, 1 and many 1. Based on range and codomain, we had two types. So if we combine them, functions can be classified into 4 categories. 1, 1 into function. The second type is 1, 1 onto function. Now 1, 1, that means injective, onto means surjective. So this is also called a bijective function. Now next you have a many 1 function. Now the fourth and the final type is many 1 onto function. Sorry, many 1 into function here and many 1 onto function. So functions can be classified into 4 categories: 1, 1 into, 1, 1 onto, many 1 into, many 1. Now let us take a simple example. Now if I am writing something like this, fr to r, where fx is equal to cos x. Now what does this mean? I have taken the domain of this function as r and the codomain also is r. So now if I draw the graph of cos x, see this kind of graph is formed. Now looking at the graph, if I draw a line parallel to x-axis, what kind of function it is? It is certainly a many 1 function. And since the codomain is the entire y-axis, now let us consider the range. So minus 1 to 1 is the range. So this becomes a many 1 into function. But on the other hand, if I write, say, like this, 0 to pi to minus 1 to 1, where fx is equal to cos x. Now let's have a look at the same graph. See, I have restricted the domain to be 0 to pi. And what about the range? Minus 1 to 1. So you can have a look. From 0 to pi, this function is decreasing. And the range is minus 1 to 1, which is certainly equal to its codomain. So that means, since it is decreasing, it becomes a 1, 1 function. And since the range is equal, so you can see from the range of this function is minus 1 to 1. So range is equal to codomain, that means it is an onto function. It is a decreasing function, so it is a 1 1 function. So it is 1 1 onto function. Now the question arises, if this is a 1 1 onto function, same function was many 1 into function. So what is the meaning? The meaning is we can convert a many 1 function to a 1 1 function by restricting the domain. Now look here, in 0 to pi I have restricted the domain and it becomes 1 1. From pi to 2 pi I could have also done like this, or I could have taken minus pi to 0. So all trigonometric functions can be converted to many 1 function, converted from many 1 to 1 1 by suitably restricting their domain. And this is true for all other functions also. But first let me talk of trigonometric functions. All trigonometric functions are considered to be 1 1 in a principal interval. Now how do you define a principal interval? See, either the interval which is nearest to origin, in which they are either increasing or decreasing, or just positive. So that is the basis. So in fact, every many 1 function can be converted to a 1 1 function by suitably restricting its domain, and every into function can be converted to an onto function by suitably restricting its codomain. Now I'll write down certain functions, say fx. If I take fx as sin x, now fx is 1 1. Fx is 1 1 if x belongs to minus pi by 2 to pi by 2. Now this is the principal interval taken into consideration. For the function cos x, the interval to be taken into consideration is 0 to pi. For tan x, this interval is minus pi by 2 to pi by 2. Now for cosec x, this interval is minus pi by 2 to 0, union 0 to pi by 2. Now for sec x, it is 0 to pi by 2, union pi by 2 to pi. Now for cot x, this is 0 to pi. So these are the principal intervals in which these trigonometric functions are considered as 1 1 functions. And you should make a note of this as well as remember this. Now let us see how it is applied in problem solving. Now let us take a small example, say fx to y, where fx is equal to, say, 2 cos square x plus root 3 times of sine 2x plus 5. Now I am asking you to find x and y, find x and y for which fx is bijective. Now tell me, if fx is to be a bijective function, now first of all you see there are terms of sine and cos present here. So what I'll do is I'll write this 2 cos square x as 1 plus cos 2x plus root 3 times of sine 2x plus 5. So this is root 3 times of sine 2x plus cos 2x plus 6. Now let us complete this. So I'll write 2 times of root 3 by 2 into sine 2x plus half cos 2x plus 6. Now this can be written as 2 times cos of pi by 6 into sine 2x plus sine pi by 6 into cos 2x and plus 6. Now this becomes 2 sine of 2x plus pi by 6 and plus 6. Now tell me, if this function sine of 2x plus pi by 6 is 1 1, then this entire function fx will be 1 1. So I'll say fx is 1 1 if and only if sine of 2x plus pi by 6 is 1 1. So sine theta is 1 1 in which interval? minus pi by 2 to pi by 2. Just now I told you. Now 2x, that means it should lie between minus of 2 pi by 3 and pi by 3. So this means x belongs to the interval minus of pi by 3 to pi by 6 on dividing both sides by 2. So this is your set x. Now what could be possibly the set y? Now what is the range of this function? Sine theta varies from minus 1 to 1. So 2 sine theta will vary from minus 2 to 2. So the range of this function will be equal to 6 minus 2 to 6 plus 2. So this is 4 to 8. So this should be your set y. So if range is equal to the codomain, then only the function becomes an onto function. So x is minus pi by 3 to pi by 6, whereas y should be 4 to 8 for this function to be 1, 1 onto. That is a bijective function. Let's take up another example. Now, again, similar type of question, but different function. Fx to y, where fx is equal to 2 to the power x into x minus 1. The question is same, what should be x and y if fx is bijective? Now, let us consider the derivative of this function. It will be 2 to the power x into x minus 1 into log 2, and then derivative of this, that is 2x minus 1. Now, for those who don't know the derivative, see, derivative of a to the power fx is always a to the power fx into f dash x into log a with respect to base. See, those who don't know, just mark it down. Now, this is always positive. This is always positive. So which one is going to be 0? See, only this is the factor which can be equal to 0. So 2x minus 1 equals to 0 at x equals to half. So if I consider this point half, now for x greater than half it is positive. So the function is increasing for x greater than half. For x less than half, if I put 0 here, you get minus 1, so it is negative. So what does it mean? It means that the function is decreasing like this and then increasing like this. So if this is your point half, now let us put this value here. So half into half minus 1. So 2 to the power half into half minus 1. That gives you 2 to the power minus 1 by 4. So this value is 2 to the power minus 1 by 4. Now look at this particular graph. See, if I consider the domain x greater than half, that means right side, it is increasing. Or minus infinity to half, this is decreasing. So function here also up to here it is 1, 1, and from here also it is 1, 1. And what should be the range of the function? The range should be 2 to the power minus 4 to infinity. So if I take x to be half to infinity and y to be 2 to the power minus 1 by 4 to infinity. See, either x is this and y is this, or x is minus infinity to half and y is the same 2 to the power minus 1 by 4 to infinity. See, in both cases your function is a bijective function. So I hope you have understood till now, and I'll be continuing with the mapping based applications and the theory behind that in the next lecture.